So in my faction game, the faction AI will go around placing settlements and buildings around the game world. That means that faction expansion and interactions with each other will be the most critical aspect of my game. So my first task is to create an algorithm that generates borders around a set of points. We want to be able to generate a polygon from these points, to check to see if something is within the borders of a given faction. And we want this polygon to be concave as opposed to being convex, so that we can avoid having large swaths of land uninhabited but claimed by a faction. To do that, we are going to be doing some geometry and trigonometry, so if anyone else is really good at this stuff and knows how to improve this in any way, please let me know. I'm sure a lot of people would be able to benefit from being able to generate concave borders around a set of points. So that's basically what this is. We want to generate a concave shape around a virtually infinite amount of points. So let's get a basic idea for the way this algorithm is going to work. So we will have our set of points that we get from getting the global positions of all our flagpoles. Then we need to create a convex shape around these points to start out, because that is a much simpler algorithm. Then we will be able to create our concave shape from that. To create our convex shape, we will use an algorithm called Delaunay triangulation. Delaunay triangulation of a set of points generates a convex hull of the points, subdivided into triangles so that none of the circumcircles of any of the triangles contain any of the points. If you want to learn more about Delaunay triangulation, I will link the Wikipedia page in the description, but I'm not going to go into how Delaunay triangulation is calculated because Godot has a built-in Delaunay triangulation function for us to use. Once we have our triangles, the idea is to shave away any of the triangles on the border of the shape that match our criteria for removal. So, we will want to identify all the bordering edges of the convex shape and all the triangles that are part of the bordering edges. Next, we will identify any of the points that lie inside the shape and not on the edges. We will call these concave points. Now we will check to see if any of our concave points are part of a bordering triangle. Any border triangles containing a concave point will be considered a concave triangle. These are the naming conventions I'll use in my code later to keep track of all these things. Now that we have a bunch of concave points, and each concave point might be part of one or more concave triangles, we will want to iterate through these concave triangles and see if any of them match our criteria for removal. This is the most important part of our concavification algorithm because there are many different ways you can determine which triangles to remove. I'm going to use what is called an edge length ratio approach. Basically, for each of the concave triangles, I will take the border edge of the triangle and get the ratio of the length of that edge to the lengths of the other two edges in the triangle. If any ratio is above a certain threshold that we choose, like 1.8, we will remove that triangle from our shape. But now, once we have removed a triangle, the shape has changed, and we need to recalculate the bordering edges, the border triangles, and the concave points, and then a new set of concave triangles. If you keep repeating this, you will eventually run out of concave points or concave triangles whose edge length ratio exceeds our threshold, at which point you would break from the loop and you would have your concave shape. Alright, so here we are in Godot. Let's start setting up our scene. Make a 3D scene. Let's save it as main. I'll add a mesh instance. Let's make it a box mesh. This will be our floor plane. I'll drag it down so it's flush with the floor. Let's make it 500 by 500 meters. I'll make a standard material so I can change the color of the floor to something like dark green. Alright, I'll add in a regular node and I'll name it flagpoles. And this will be the parent of all the flagpoles we use to represent things like settlements and buildings for a given faction. So I'll make a little flagpole here by adding in another mesh instance. I'll do another box mesh, and I'll drag it up so it is above ground. And let's make it 0.1 by 0.1. There we go, that's our flagpole. Now I'll just rename it to flagpole. So to simulate our points of interest around the world, I'll just copy and paste these around a few times, just so it looks like how these points of interest might actually be distributed during our game. And this is kind of the main point of the algorithm, so it can basically take any amount of points. So this looks pretty good. I'm just going to move them around a little bit so you can kind of see how the concave contours might end up looking. So now that we have our flagpoles, I'll add a canvas layer node so that we can draw our 2D shapes on the screen. I'll just name it UI. And now I'll go here and add a camera 2D so we can see our shapes when we run the scene. Then I'll add a control node so I can kind of control the position of the shapes that appear on the screen. And I'll make all the shapes we create a child of this. So now let's start working on our script. I'll go to the root node of the scene and add a script, and I'll call it main.gd. I'll make a reference to that UI control node. So first, to draw our shapes on the screen, I'll make a line function that takes point A and point B as parameters. And I'll make a polygon function that takes an array of points as a parameter. In the line function, I'll make a new line 2D. And we'll set the points of that line to a packed vector 2 array, like this. But if we leave it like this, when it draws the shapes on the screen, it will convert the real-world distance units in Godot, which is meters, directly into pixels on the screen. So that means 1 meter in our game world will convert to 1 pixel on the screen. And it will draw our objects super small. So I need to scale these points up by, let's say, 50, so they appear bigger on our screen. And I'll set my line width to 10 pixels. And then you can just do UI.addChild, then line. So now for the polygon, we'll do kind of the same thing. We'll still need to scale the points, so I'll make an empty array called scaled points, and we'll actually make it a packed vector 2 array. So now we'll iterate through the points, and we'll add the scaled point. Now we'll create a new polygon 2D. And now we'll set the points of the polygon to scaled points. And then we can add it to our UI. Alright, so now that we have those functions set up, let's go ahead and create our generate borders function. Alright, so the first thing I'm going to want to do is clear the UI every time this function is called. For I in UI.getChildren, and then UI.removeChild I. So now I want to get the global positions of all those flagpoles. So first I need a reference to that flagpoles group node I made. And we'll want to get all the children of that flagpoles node. We'll make a function called getPointsFromFlagpoles. And it will take the array of flagpoles as a parameter. We'll go down here and start setting up that function. I'll make an empty packed vector 2 array called points. And then for each flag in flagpoles. And then we'll add the global position of each flagpole to points. Using just the X and Z coordinates. And then we just return points. So now that we have the points from our flagpoles, we have to triangulate them to get a convex shape around the points. So back up here in the generate borders function, I'll make a variable called triangles. And we're going to make a new function called getDelaunay_triangles, which takes the set of points as a parameter. So now let's go down here and start making that function. So the first thing we can do is go right ahead and triangulate these points using geometry 2D dot triangulate Delaunay. And what this function will return for us is an array of indices representing the faces of the triangle. These indices can be iterated through and passed back into the original points array to get the data for each of the triangles generated by this function. So if we want to use this array of triangle indices to get an array of triangles where each triangle is an array of 3 vertices, I'll make a variable called triangles. And then we can just iterate through the triangulate variable in groups of 3 like this. And then here we'll make a new variable called triangle. And then we'll set it to be an empty packed vector 2 array. And then for each point of the triangle, and then we can get our coordinates by passing in the triangulate value into the points array. And then we can just use this formula to get the correct triangulate index while still iterating through the 3 points up here in this for loop. Now we can append that point to our triangle array, and then append that triangle to our triangles array. And then we can return triangles. So now let's try to visualize this on the screen. So I'll add in the ready function. And then call generate borders. And then I'll just print triangles so you can see. And here you can see that we are generating a 2D array with all the vertices of the triangles. So now we have triangles that all together make a convex shape around all of our points. I can visualize this right now if I want by using our line function. We iterate through each triangle in triangles. And then for each point we have, we can use this expression to get that edge of the triangle. It just takes the current index of triangle as the first point of our edge. And then for the second point, we do the current index plus 1, and then remainder 3, so that it wraps around to the beginning when we get to the end. So now I can go ahead and use our line function we created earlier, passing in the first element of edge and then the last element of edge. Now let's hit play and see if we can see the triangles. Alrighty, so now you can kind of see how these triangles form a convex shape around the set of points. So now what we're going to want to do is extract the bordering edges of this shape from the triangles array. I'll make a new variable called boundaries, and then we'll make a new function called getBoundaries that takes the array of triangles as a parameter. So now let's go down and start making our getBoundaries function. So we can basically find out which of the triangle edges are on the border of the entire shape by extracting the edges that only occur once in the array of triangles. For our array of triangles, all the edges that touch each other appear twice, while edges on the border of the shape will only ever occur once. So we can do this by first making an empty array called edges, and then another one called outer edges, and another one called inner edges. So now let's iterate through each triangle, and we can get our edge the same way we did before. So that gives us our edge. And now I'll run edge.sort so I can sort the vertices for consistency. And now I'll append this edge to edges. Now I'll make an empty dictionary called edge occurrences. And we'll iterate through each edge. And if edge occurrences already contains this edge, then we will increase the amount of edge occurrences for that edge by 1. And those would be all the edges that exist on the inside of our shape. And then else, edge occurrences is equal to 1. So now we want to separate our edges into those two different groups based on the amount of edge occurrences. So we can do for_key in edge occurrences.keys, which returns the actual edges themselves. If edge occurrences equals 1, then we add that edge to outer edges. Otherwise, if it occurs twice, we add it to inner edges. So to visualize this, I'm going to do for edge in outer edges. And then our line function. And then we can just return outer edges. So let's run it and see what we get. And right there you can see our boundaries. So now that we have our boundaries, we want to get our boundary triangles. So we'll make a new function called getBoundaryTriangles, and it's going to take triangles and boundaries as parameters. So now let's go down here and make that function. So I'll just make an empty array called boundary triangles. Now we can iterate through each triangle, and then through each point, and we can get our edge. And then we'll sort the edges just in case. So then, if boundaries has edge, then we can add that triangle to boundary triangles. So now to visualize boundary triangles, we can do for triangle in boundary triangles, and then we can use our polygon function. And then we can just return boundary triangles. So now let's run it and see what we get. Okay, I did something wrong. Oh, there we go. I was putting triangles instead of triangle. Okay, so now let's hit play. And there we go, there are our boundary triangles. Alright, so now let's go back up to the generate borders function. Now that we have our boundary triangles, the next thing we're going to want to find are our concave points. So I'll make a get concave points function that takes points and boundaries as parameters. So now we'll go down here and start making that function. We'll do more of what we've been doing and make an empty array called concave points. Alright, so the concave points are going to be all the points that exist inside our shape that our boundaries create. So if we wanted, we could try to check to see if any given point is inside of our array of points by directly using geometry2d.isPointInPolygon with our point and our points array as arguments. But there's two problems if we do that. To form the polygon used in geometry2d.isPointInPolygon, it takes the array of points that you pass into the function and connects them from first element to second, second to third, third to fourth, and so on. So it connects the points in the order they appear in the array. So if the vertices for our boundaries are ever not in the correct order for any reason, the polygon shape will not be calculated correctly, and we won't get our list of concave points. And then the other problem we have is that geometry2d.isPointInPolygon will return true for any points that actually exist on the edge of the shape. This doesn't work because we want concave points to return all the points that exist inside the shape and not on the edges of it. So that being said, there's a few things that we need to do before using geometry2d.isPointInPolygon. First, we want to sort the vertices and edges of the shape in a clockwise order around a given center point that we will find. And then, to exclude any points on the border of the shape, we'll create a new deflated shape by scaling down each of the points just a little bit in the direction of their vertex normals. So I'm going to need to start setting up a few new functions. First, we'll make a variable called sorted points, and then a variable called sorted edges. And then we'll set up a function called sort vertices that takes the boundaries as a parameter. And then we'll make the function called sort edges that takes the sorted points as a parameter. So now I'll go down here and start working on our sort vertices function. Alright, so to sort our points in a clockwise direction, we need to compare the angles from each point to a given center point and sort the points in order based on those angles. So I'm going to make an empty array called vertices, and then I'll make a dictionary called unique vertices because I want to extract all the unique vertices from the list of edges. So for edge in boundaries, And then for vertex and edge, if the vertex is not in our array of vertices already, then we can add our vertex to vertices. So that gives us an array of all the unique vertices in our boundaries. So now we need to calculate the center point of our shape, and we can do that by finding the average of all the points of the shape. So we'll make a variable called center and just set it to vector2, 0. And then for each vertex in vertices, we can add the vertex coordinate to our center vector. And then at the end, we can divide center by the amount of vertices to get our actual center point. So now let's calculate the angles of all the vertices to that center point. I'll make an empty dictionary called angles. So now for each vertex in vertices, we can calculate the angle to the center point with this formula. Arctangent 2, vertex y minus center y, and vertex x minus center x. And then we can add the angle to angles using the vertex as the key. So now we can start sorting the vertices based on these angles. To do that, we can do vertices.sortCustom, which takes a callable function, and we can do a lambda expression by writing func vertex 1, vertex 2, and this is going to sort any two vertices based on this true or false condition, return, and then return true if angle 1 is greater than angle 2. And this essentially results in vertex 1 being placed before vertex 2 in our array if its angle is greater. So now, just so you can see, I'll go ahead and print our sorted points. And then we'll run our scene. So now down here we have our boundary vertices sorted in a clockwise order. So now we want to use our sorted points to get an array of sorted edges. So now I'll go down here and make the sort edges function. And again, I'll make an empty sorted edges array. Then I'll iterate through each vertex. So we're basically just going to be turning this array of sorted vertices into an array of sorted edges. So I'll get our current vertex, and then we'll get our next index, kind of using the same method that we use to construct our edges using the remainder operator. I can do I plus 1 remainder sorted points dot size. So that gives us our next index, and now we can get our next vertex doing sorted points next index. Then we can just start constructing our edge like this. Current vertex and next vertex. And then just add the edge to sorted edges. And then we can just return sorted edges. So now if we go up to our concave points function, now that we have sorted points and sorted edges, now what we're going to want to do is make a deflated shape by scaling down the points along their vertex normals by a small amount that we'll call scale factor. So I'll make a variable called deflated shape, and we'll make a new function called scale points by normals that takes the sorted points, the sorted edges, and a float value as the scale factor. We'll do 0.1 and make it negative so that it shrinks the shape. So now we'll start working on this scale points by normals function. Once again, I'll make an empty array called scaled points. In order to scale the points, I need to find the vertex normal of each point. So we'll do var vertex normals, and we'll make a new function called getVertexNormals, and it'll take the sorted points and sorted edges as parameters. So now I'll go down and start working on the getVertexNormals function. I'll make an empty array called vertex normals. So now let's think about it. What even is a vertex normal? And how would it be calculated? Put simply, what we refer to as a vertex normal is basically just the normalized average of the two adjacent edge normals. And the edge normals are basically just the cross product of the edge itself. This is why it was important to sort our edges and vertices, because edges that go in opposite directions will have normals in opposite directions. And we want every normal to be going in the same way. So if we want to calculate the vertex normals, we need to get the edge normals. So I'll make an empty edge normals array. So then for each edge, I need to find its normal with a new function called getEdgeNormal, and we will pass into it sorted edges at the current index. So now let's go down and start working on this getEdgeNormal function. I'll get the starting vertex of the edge and then the end vertex, and we can start out by getting the direction of the edge, which is just the distance from the start vertex to the end index normalized. So we can do direction equals end minus start, and then we can normalize it. So now we can get the normal by swapping the x and y components of the direction and then making the x component negative. And then we'll normalize it so it is unit length. Now let's visualize this with our line function by doing the starting vertex and then the starting vertex plus the normal. And then I'll also return the edge normal. And then I'll also use the line function to show the boundaries themselves so the normals kind of make more sense. And now we'll hit run, and look at that. Now you can see that each edge has its normal direction, and now we can use these to calculate our vertex normal direction. So now we can go back up to the getVertexNormals function. Now that we have the edge normals, I can go through and calculate the vertex normal for each vertex. So now let's get the previous index, kind of like how we did before. We'll do I minus 1 plus sorted edges dot size, and then remainder sorted edges dot size. So that will give us the previous index for whatever point we're on. And then we'll get our previous edge normal with edge normals previous index. So now we have our previous normal, and then we're going to want our current edge normal, but we'll just leave that null for now, because if current index is the final index, we want to set current edge normal to be the first edge normal in the array. Otherwise, we set current normal to edge normals current index. This way it all wraps around the way we want it to. And then we can calculate our vertex normal by doing current normal plus previous normal normalized. So that gives us our vertex normal. So now we can go ahead and add that to vertex normals array, and then we can just return vertex normals. So now let's see it by using our line function. So now let's see what we get. There we go. Now we have our vertex normals. So these are the directions that we want to scale each point down along. Going back up now to our scaled points by normals function. Now we'll iterate through all our points. And scale them by our scale factor. We'll do scaled point equals our original point plus our vertex normal times our scale factor. And then we'll just add that scaled point to scaled points. And then return scaled points. So now if we go back up to our concave points function, we have our deflated points. So now we'll iterate through our points again and check to see if the point is concave using geometry 2D .is point in polygon. And we'll want to check our original point against our deflated point set. So then, if point is concave, we can go ahead and add that point to concave points. And then we can return concave points. So now I'll go here and print concave points, and when we hit run, here you can see the positions of all the concave points. So now that we have our concave points, we can start going through our loop that actually removes concave triangles from our shape. And we'll want to remove any of the concave triangles whose border edge length ratio exceeds a certain threshold. At first you might think that we should start a for loop to iterate through our concave points, and then iterate through our concave triangles. But the problem with this is if we get to a concave triangle that is supposed to be removed, then we have to recalculate the borders, the border triangles, and the concave points again. And we wouldn't be able to modify the concave points array from inside of the for loop that's iterating through it. So instead of a for loop, we'll use a while loop. But first, I'll make a current index variable and set it to 0, so we can still iterate through concave points manually in our while loop. I'll put while concave points.size is greater than 0. So if at any point there are no more concave points, we'll break from the loop. Alright, so we'll get our current concave point with concave points current index. So now, here in this while loop, we want to get an array of all the concave triangles for the current concave point. So we will do concave triangles and create a new function called getConcaveTriangles, and it will take the concave point and boundary triangles as parameters. So now let's go down here and make the getConcaveTriangles function. We'll make an empty concave triangles array, and then for triangle in boundary triangles, if triangle has the concave point, then we want to add triangle to concave triangles. And then let's return concave triangles. So now we have the concave triangles for that concave point. So now that we have our concave triangles, we can start going through and removing them. I'll make another while loop while concave triangles.size is greater than 0, so that if concave triangles is ever empty, we break from this loop. So what I'll do is I'll take our original array of triangles, and then we'll make a function called removeTriangles that will remove any triangles with an edge length ratio greater than our ratio threshold, and then return a new array of triangles if any were removed. Otherwise, we just return the original array of triangles. So for parameters, it'll take the triangles array concave triangles, and boundaries. So now let's go down and make this remove triangles function. Alright, so let's define our ratio threshold. After doing some testing, I found that 1.8 worked pretty well for me. So now we can start iterating through our concave triangles. So for triangle in concave triangles. So even this loop we'll have to break from if one of the triangles gets marked for removal. So in order to keep track of whether or not a triangle was removed during our while loop, I can go up here and make a global variable called triangle was removed, and we'll set it to false by default. So now before we are moving on to the next triangle in this for loop, if triangle was removed, then we break from the loop. So then otherwise we can make an empty array called edge lengths, and that'll just have the lengths of all the edges of the triangles. And then I'll make a variable to store which edge is our boundary edge. So now we'll iterate through our edges again and get our edge the same way we've been getting it. And then we'll sort the edge again. Then edge length equals the first element of edge dot distance to the second element. So now we have our edge length. So we'll add it to our edge lengths array. And now we have an array of edge lengths. And then if boundaries has the edge, then that is our boundary edge. So now that we have our boundary edge, we can do if boundary edge. We'll calculate the length of the boundary edge. And then we want to get the other edges by iterating through edge lengths. And if the edge length doesn't match the boundary edge length, then we put those edges in other edges. So now that we have our other edge lengths, we can calculate their ratios to that boundary edge length. So var ratio 1 equals boundary edge length over other edge length 1, and then ratio 2 equals boundary edge length over other edge length 2. So now that we have our ratios, we can see if either of them exceed our ratio threshold. So if ratio 1 is greater than ratio threshold, or ratio 2 is greater than ratio threshold, then we would want to remove this triangle from our original list of triangles. So we'll do for try in triangles, and then I'll turn my triangle into a packed vector 2 array so we can compare them. Then I'm going to sort the elements of both triangles I'm trying to compare. And then if triangle equals triangle array, then we want to remove that triangle from triangles. So triangles.erase triangle. And then we're going to want to set that triangle was removed flag to true. And then we'll want to break from the loop. And then return that original array of triangles, which will have been modified if any of the triangles were removed. So now we can go all the way back to here. So now we have our remove triangles function. Let's go back up here now. So now after that, if triangle was removed, we'll want to recalculate everything. So first we have to recalculate boundaries, then boundary triangles, and then concave points. And then if a triangle was removed, we'll want to reset the current index back to 0. And then, regardless of whether or not a triangle was removed, we'll want to break from the while concave triangles dot size is greater than 0 loop. So now, if triangle was removed, we want to set the triangle was removed flag back to false. And then, if the next index is the final index, this is where we would want to return the final shape and exit from our whole loop. But for now, I'm just going to draw it on our screen using 4 try and triangles and make a polygon for each triangle. And then lastly, if the next index is less than concave points dot size, then we'll want to increment our current index by 1 for the next iteration of the concave points while loop. Otherwise, we set the current index back to 0. And it looks like I messed something up. Okay, so here in get concave triangles, I was appending the concave point and not the concave triangle. Alright, so now we have an infinite loop, so there's one more thing to fix. Back here, where you return the final shape, you would also need to break from the loop. Otherwise, you just get stuck in an infinite loop. So now let's try running it. And look at that. That looks to me like our concave shape. You can see that it forms a natural looking shape around the set of points. Now we can play around with the flagpoles and see how it affects our shape. So I can copy and paste these flagpoles around and see how our shape evolves. So now here you can see I got like 100 of them or so. Now we'll run it and see what it looks like. And that looks pretty good. You can see it follows the shape of the points pretty well, no matter how many points we have. So I hope this algorithm is useful to a lot of people out there. And if anyone finds any ways to make this algorithm simpler and better in any way, please let me know. This is just how I got it to work for me.